In this presentation, we have to talk about quantum tunneling. See, a rectangular potential barrier is shown in figure. The height of the barrier is V0 and the width of the barrier is A. Suppose the energy of the particle is lesser than the height of the barrier. Here is the energy. In the classical view, there is no probability for the particle to make its forward journey. Compulsorily, the particle should be reflected back. But on the case of quantum view, there is some probability for the particle to make its forward journey without reflection by the way of quantum tunneling. To describe this problem, quantum tunneling, we should choose the Schrodinger time independent wave equation, since the potential is not a function of time. Now we have to develop the Schrodinger equation for the three regions. This is the first region, this is the second region, and this is third region. Both first and the third regions, the value of potential is 0. The potential of region 2 is V0. Now we have to develop the Schrodinger equation for the region 1 with the condition of potential V equal to 0, then the value of x is greater than minus infinity and less than 0. This is the condition for 0 potential. See, the value of V is here, the left hand side of the barrier is 0. The value of x is greater than infinity, less than 0, which means that outside the barrier, the left hand side we are concentrating. So for this region, the Schrodinger equation is d square psi 1 divided by dx square plus 2m e by h cross square into psi 1 is equal to 0. This is equation number 1. Here the value of v equal to 0, so I have discovered. If you put k1 square is equal to 2me by h cross square, then the above equation is changed as d square psi 1 divided by dx square plus k1 square into psi 1 is equal to 0. Now the solution for this equation 2 is psi 1 of x, which is equal to a into e power I k1x plus b into e power minus I k1x. This is equation number 3. Here a into e power I k1x is incident wave, b into e power minus I k1x is a reflected wave. Now we have to develop the Schrodinger equation for the region 2. For the region 2, the potential is V0, then the value of x is greater than 0, less than e, which means that we are talking about the width of the barrier. For this region, the Schrodinger equation is d square psi 2 divided by dx square minus 2m by h cross square v0 minus e into psi 2 equal to 0. Because here the energy of the particle is lesser than the width of the barrier. So that we have modified this minus e of h cross square to v0 minus e into psi 2. This is equation number 4. If k2 square is equal to 2m by h cross square into v0 minus e, now we may modify this equation 4 in this form: d square psi 2 divided by dx square minus k2 square into psi 2 is equal to 0. This is equation number 5. Then the solution of equation 5 is psi 2 of x equal to c into e power minus k2x plus b into e power k2x. This is equation 6. Here c and d are the constants which have to be evaluated. In the first region also you have two constants a and b, and the values have to be evaluated. This is the detail about the region 2. Now we have to go for the third region. For the third region, the potential is 0. At that region, the value of x is greater than a but less than plus infinity, which means that the particle is coming out of the barrier, which is available in the third region. So for the third region, the Schrodinger equation is d square psi 3 divided by dx square plus 2m by h cross square e into psi 3 equal to 0. This is equation number 7. Here k1 square is equal to 2me by h cross square. Therefore, d square psi 3 divided by dx square plus k1 square into psi 3 equal to 0. This is equation number 8. Then the solution is psi 3 of x, which is equal to f into e power I k1x plus g into e power minus I k1x. But the reflected component is not present in the third region. Therefore, the exact solution is psi 3 of x, which is equal to f into e power I k1x. This is equation number 9. So this is a equation for the third region. Now we have to solve the values of the constants a, b, c, d and f by the way of applying the boundary conditions. Now we should apply the boundary conditions. The first boundary condition is the wave function psi must be continuous at x equal to 0 and x equal to a. This is the first boundary condition. Then psi 1 of x equal to psi 2 of x at x equal to 0. This is one case. And another case is psi 2 of x equal to psi 3 of x at x equal to a. Because at x equal to 0 we have to consider the two wave functions psi 1 and psi 2. And another end is a. One end of the barrier is 0 and another end of the barrier is a. So at that end we have to consider on two wave functions psi 2 and psi 3. Psi 1 of x is known to you a e power I k1x plus b into e power minus I k1x. This is psi 1 of x. This is equal to c into e power minus k2x plus d into e power plus k2x or near k2x. This is the values of psi 1 of x and psi 2 of x. Now apply the condition at x equal to 0. If you put x equal to 0, this is a e power I k1 into 0 plus b into e power minus I k1 into 0 is equal to c into e power minus k2 into 0 plus b into e power k2 into 0. This gives a plus b, which is equal to c plus d. This is equation number 9 because equal to 0, 1. If we come to this region, psi 2 of x equal to psi 3 of x. For that, we should write the value of psi 2 of x. Psi 2 of x is c into e power minus k2x plus b into e power k2x. Then psi 3 of x is f into e power I k1x. If we put x equal to a, then c into e power minus k2a plus d into e power k2a, which is equal to f into e power I k1a. This is equation number 10. Just we have applied this one in the direct way. The next boundary condition is the first derivative. The first derivative of the wave functions first derivatives of the psi must be continuous at x equal to 0 and x equal to a. So this is the second boundary condition we have to apply. First derivative means dψ by dx. We know the values of psi 1 of x and psi 2 of x. Then you can apply the boundary condition d psi 1 by dx equal to d psi 2 by dx at x equal to 0. This is the boundary condition we have to apply for these two wave functions. Then d psi 1 of x means ik1 a e power ik1x minus ik1 b e power minus ik1x. This is the value of d psi 1 by dx. This is equal to minus k2 c into e power minus k2x plus k2 d into e power k2x. Here we have to put x equal to 0. Then ik1a minus ik1b, which is equal to minus k2c plus k2 into d. See this ik1 into a minus b is equal to minus k2 into c minus d. From this we can write a minus b, which is equal to minus k2 by ik1 into c minus d is a minus b, which is equal to I k2 by k1 into c minus d. This is our equation 12. So we have arrived at the value of a minus c by the way of applying the boundary condition d psi 1 by dx equal to d psi 2 by dx at x equal to 0. Then the next boundary condition is d psi 2 by dx equal to d psi 3 by dx at x equal to a. In the previous case, d psi 1 by dx equal to d psi 2 by dx, we have put the boundary condition x equal to 0. For d psi 2 by dx equal to d psi 3 by dx, we have to put the boundary condition x equal to a. You know that psi 2 of x equal to c e power minus k to x plus d into e power k to x. Therefore, d psi 2 by dx equal to minus k2 c into e power minus k to x plus k2 d into e power k to x. Then psi 3 of x is equal to f into e power I k1x. This is equal to d psi 3 by dx equal to I k1 f into e power I k1x. Just to psi 2 of x I have written c to e power minus k to x plus d into e power k to x. D psi 2 by dx equal to minus k2 c e power minus k to x plus k2 into d e power k to x. Psi 3 of x is f into e power I k1x. Then d psi 3 by dx equal to I k1 f into e power I k1x. Now apply this boundary condition. D psi 2 by dx at x equal to a. So minus k2 c e power minus k2 x. Instead of x we have to put a minus k2 a plus k2 d into e power k2a equal to this value d psi 3 by dx at x equal to a. We have to substitute this value. This is I k1 f into e power I k1 a. Now this is minus c e power minus k2a plus d into e power k2a, which is equal to I k1 by k2 f into e power I k1a. This is our equation 13. See that with the help of all these equations, we have to get the values of a, b, c, d and f. We have to continue the same in the next part. Thank you.